Hello, my name is Gennady and I'd like to present a paper on the design and implementation of routing control platform. This paper was written by authors Matthew Caesar, Donald Caldwell, Nick Feimster, Jennifer Rexford, Aman Saik, Jacob Swen Diermeier. It was published in SDI 2005. So before we get into this presentation, I'd like to go over some of the definitions. IP stands for Internet Protocol. AS acronym stands for Autonomous Systems. Basically, autonomous system is a collection of connected uh, IP routing prefixes under control of single administrative domain. A BGP is the Borderway Gateway Protocol. It is Internet's interdomain routing protocol. It is designed for controlling traffic between autonomous systems. It uses global knowledge to assign single best routes for each prefix to each router using IBGP, which we'll define later. It is a path vector based protocol. Each network adds its own autonomous systems. each network adds its own autonomous system to the path prior to propagating announcement to the next domain. So it creates a path vector or a route, which way to route information. Its current version is 4 and it had more than 20 revisions. IBGP stands for Internal Borderway Gateway Protocol. It's exactly the same protocol. The only difference is that this protocol is run within the autonomous system. eBGP is the External Borderway Gateway Protocol. Again, it's exactly the same protocol, but it's used for connecting between external autonomous systems or neighbors or peers. IGP is the Interior Gateway Protocol. It's a router discovery protocol within autonomous system used for discovering uh, routers within an autonomous system. For example, there are two well-known protocols for doing that: using reliable flooding, OSPF and ISIS. Looks like ISIS. Then there is another called hot potato. It's choosing the lowest cost path from multiple BGP routes. So the motivation behind this research was that there is a significant growth of a routing table within autonomous systems. This rapid growth could be attributed to internet-enabled devices, mobile devices, or the significant growth of them. That these devices add significant change, or at least dynamic. There is dynamic route computations. For example, somebody talking on a cell phone now, and they're driving in a car, and that cell phone has to have multiple towers, so this routing has to be done at runtime, and it introduces also significant computational complexity, because these routes may now span not only within the same network. Now they could jump potentially between different competitive towers who are under completely entire different autonomous systems. So just as an example, also Internet of Things, this is a more recent phenomenon, which wasn't really done at the time of the paper was written, but it's right now it's one of the major things that really affecting the routing table, as pretty much every appliance or right now being designed has to be internet enabled for some reason. Also, this creates a vicious cycle. Basically, all these services and everything that we use, uh, the more we use it, the more we depend on it, and then the bigger it grows, and the bigger it grows, then we have to use it even more, and so on. So this creates a very large cycle. And another issue is that the bigger the network, the more chaos and churn that they produce. So this is a very challenging problem. For example, so the current solutions is the BGP routing, and the design for it within autonomous systems is unfortunately somewhat inefficient. It relies on specialized hardware. It is very expensive to upgrade. Um, there is a rapid growth of the routing table, and these specialized hardware typically have a fixed amount of memory, and when it reaches beginning to reach its threshold, um, it has to rely so so it relies on full mesh routing, having a complete view of all routes, and this full mesh routing problem has is a scalability issue. It's extremely expensive to maintain, and with the explosive table growth, um, this becomes and the limited fixed amount of memory that these specialized hardware devices have, it becomes a problem, and routers can start behaving unpredictably, dropping routes and exhibiting various uh, behaviors. And what we see here in table one is actually the BGP route selection algorithm for computing uh, optimal routes. And basically, this is a multi-step process designed to so the first few steps, what it does is it chooses the lowest cost paths, and after that, there may be several. Typically, will be several paths that are of the same cost, and the other attributes are basically designed to just narrow down to a single route. If you have two or more routes that are competing for the lowest cost path, and the cost is the same, then these attributes will definitely the last attribute with the lowest ID number, because they're all unique, would certainly narrow down to a single path. Okay, so as somewhat mentioned a little bit earlier, very large networks were not really considered um, when the protocol IBG or the BGP was designed, and as mentioned previously, had over 20 iterations or revisions to it. It's currently on version 4, official version 4. Um, so one of the things that, or at least one of the solutions that was proposed, how to deal with scalability issue of the routing tables, and how to address that, was the routing reflections. So the solution is basically configuring multiple routers in a hierarchy, and using the IBGP, the Internal Border Gateway Protocol, basically to streamline or reduce the computational, or to slice up the traffic. Uh, Basically, this approach is typically done within large networks, and it addresses the scalability issue. Also, what it does is significantly reduces memory for each one of the routers. It reduces the connectivity overhead. However, there is a cost to this, and one of the costs is that because now each router doesn't have the full mesh view of the entire network, it only has a limited view. So very likely the chosen routes will be suboptimal. And another downside to this is it can produce protocol oscillations, meaning that one event, like a route being dropped or a router being withdrawn, will cause a lot of traffic being generated in the route recalculations and so on, and then it will cause another, and so on, so going back and forth. So another limitation is that BGP is the behavior is pretty difficult to predict, especially when it's under full load. Under full load, it's difficult to predict behavior. so, so the design considerations for the approach for designing this or addressing this problem is that yeah, the solution must handle scalability or be on par of route reflectors. Also, having capability must be able to have correct routing behavior under full workload. Also, run on commodity hardware, uh, and minimize change and interoperate with existing infrastructure. The reason for the last two bullet points is that typically autonomous systems, they're owned by entities that are non-related entities, and each entity that owns them could be commercial or state or educational, and they don't have agreements with them or nor financial incentives to make upgrades or make changes to them. So all of them are, most of them are financially or politically or educationally motivated, like the ownership. So they have various incentives, and they run this somewhat standardized BGP protocol, and it would be very difficult to get everybody to upgrade. So the solution must be able to interoperate with the existing infrastructure, while still at the same time at least address all these issues within this autonomous system. So the proposed solution is called Routing Control Protocol, RCP. So the solution again is logically centralized design, but it can be distributed to increase uh, routing capacity, maybe not so much capacity, but more resiliency, I think would be a correct word. So the point here is to also makes per router routing decisions for the entire network in real time also. And another one is assign single best BGP route for each prefix to each router and distribute routes using IBGP protocol. So the authors had two primary goals: is to provide intrinsic connectedness of full mesh IBGP, while at the same time also provide fast response to the network events. And this is actually going to be an issue. We'll see it later on. So this architecture design consists of three primary components: IGP viewer, BGP engine, and the RCS, route control server. So the IGP viewer, basically its purpose is to monitor the IGP topology and to provide that information to the route control server. So IGP viewer basically is configured with large IGP link weights. And the reason for those weights is to ensure that no router will try to route its packets through IGP viewer uh, as a shortcut, potential shortcut. So because the whole purpose of IGP viewer is to monitor topology changes and to provide that information to the RCS. so so what it does, what the way it does is RGP viewer listens for the link state advertisements, and it basically receives these advertisements using the reliable flooding from all routers within the partition. Um, Basically, it gathers a complete IGP topology for all partitions that it connects with. And what it does once it gets what it does is it actually computes pairwise shortest paths for all routers within an autonomous system. So a BGP engine is its purpose is to basically learn BGP routes and to provide that information to the route control server, and at the same time also distribute these best paths to other routers. So the first thing what it does is essentially establish IBGP sessions to all routers in the IGP partition. And as you recall, IBGP is exactly the same BGP protocol, but it's just internal within autonomous system. And it communicates its routing assignments. So once it gathers these messages, it sends them to the route control server, which computes the optimal routes for each router, and then it pushes back to the BGP engine. And then BGP engine, what it does is communicates those best routing paths for each router. So routers interact with BGP engine using again standard BGP, uh, and this way it maintains compatibility with existing hardware. So the second to the last bullet can send different routes to each router. What this one means is that unlike in the previous example where we had um, let's see, what was this? Uh, Route reflectors. The solution was the BGP solution was with route reflectors. Um, when they divvy up this traffic into this hierarchy, they were forced to use specific routes as opposed to um, BGP engine, which is not bound to those uh, constraints. So we can send routes as actually best routes to the routers. So in addition, also what it does is it sends updates only if there is a change in routing. So again, minimizing communication. So some of the optimizations for the BGP engine is to uh, uh, is to reduce network communications and provide fast recovery for efficient refresh. What it does is stores BGP routing tables in local routing information base cache and routing information base output cache. So so RIB-in basically can be used, for example, if the RCS fails, and RCS, as we've seen, basically routing control server in our three-component design, because what it does, this thing does is computes optimal routes for everything else, and uh, as we can see, for one of the optimizations is that in case of a failure or there is a new RCS being brought up, the BGP engine can actually read this data from its own cache and provide it to the router without having to resend or requery its peer routers that it's interacting with. So the RIB out, for example, similarly can be used to resend route assignments without having to requery the RCS. Again, so these optimizations actually significantly reduce the workload in potential churn, like network churn. Or so let's see. So the route control server is basically like the maintains the global view or the full mesh, yeah, as in BGP routing scheme. Basically, what it does is it's responsible for aggregating internal and external routing information and computing optimal routes for a group of routers. Okay, so the first thing what it does is gathers IGP topology from IGP viewer, and second thing it does is also it gathers the BGP routes from the BGP engine. Then it takes those two and computes a global most like optimal paths. Um, and once it computes those paths, it uses that information to push it back to the BGP engine. And then BGP engine is the one that's responsible for notifying all the routers of the optimal paths. And it only assigns those routes only if they're better, in case they're better. Um, yep, okay, mentioned the okay, mentioned that one. Okay, so each replica, RCS replica, makes routing decisions for partition that it has complete IGP topology. And this solution, the RCP architecture, can actually have it requires at least one instance of an IGP viewer, at least one instance of BGP engine, and at least one instance of a routing control server. But you can have, for resiliency purposes, you can have multiple versions of these things, and we'll discuss the resiliency a bit later on. Okay. Okay, so optimization. So the routing control server optimization again. So instead of storing every single uh, BGP route, what it does is it stores only one copy for each BGP route, and it does this with RAB in cache table, and it also this significantly reduces the memory of the routing table. um, Also, another thing is that for each routing path, what it does, each routing path, it keeps track of dependencies, meaning that uh, if if a particular path needs to get changed, there are pointers in a or the dependencies uh, within that path can show what else, who were the dependents or other routers that were depending on that particular path that is no longer available. So this provides a fast way to recompute each any route. So this is another optimization that significantly reduced the computational cost of having to recompute everything else, or at least significantly reduces the computation time for path recomputation. Um, Another optimization is that it uses groups or combines routers into groups and then sends them the optimal paths. So this way, the paths it doesn't have to compute for every single router. So one way for this infrastructure to interact with existing uh, architecture was to actually implement or keep or emulate full mesh BGP. And this is actually the way it's emulated is that it's using the same rules as we seen earlier. And let's see those rules. Okay, this is table 1 again that shows these rules basically for choosing which routes are optimal, and this is going to be exactly the same scheme that was shown earlier that BGP uses for optimal route computation. And because we're using exactly the same scheme, we're guaranteeing that because of the global view that we collect, that the BGP engine collects and passes to the RCS, and since we're using the same scheme to compute the routes, we're guaranteed to get uh, exact same optimal routes as in traditional BGP. And basically, these are two key properties of RCP. Is that we have route validity. We do not assign routes that can create forward loops, black holes, or other anomalies. And then second property is path visibility. So every router should be able to exchange routes with at least one RCS. As mentioned previously, the RCP can have multiple, at least if it has more than one component of the three components: the IGP viewer, the BGP engine, and RCS. If it has more than one RCS, then there is a potential for consistency problem, and they present a scheme for reducing consistencies or inconsistencies, and they rely on a deterministic routing computation protocol. And if multiple RCS replicas have IGP connectivity to some router in a system, then it's going to be up to those replicas to make sure that the path assignment that there is they come to the same path assignment for that router. And well, as I'm going to point out later, I'll point it out later. Okay. So to test out their to test out this infrastructure, this is the following their major points for. So the test emphasis were scalability and efficiency, and they utilized traces of BGP traffic and internal routing data from Tier 1 backbone. And the data set was gathered on August 1st, 2004. And I believe this was 24-hour snapshot. They point out that typical autonomous system is pretty big. It has anywhere from 500 to 1,000 routers. Interestingly, the dashes are missing for some reason, but they are in the source code. Anyways, so the typical autonomous system is big. It has between 500 to 1,000 routers, and it has from 150 to 200,000 prefixes to deal with. Um, this is this was done. These numbers were done in 2004, and reading more recent papers, the routing tables are in a 600,000 prefixes range. So 3 times increase. Okay, and they used 3 types of uh, uh, testing. They used white box, and black box real time. Um, so the white box testing, what they used was they measured time and memory usage of the RCS functions. For the black box with no queuing, they measured additional overhead of the message passing protocol. Basically, what they did was timing, playing back one message at a time, and timed how much overhead it cost within the RCS framework. And the black box real time, basically, they measured in real time how by replaying all the messages based on the original timestamps. Okay, so uh, when they're measuring RCS, OSPF viewer, as we mentioned, OSPF is flooding protocol within it's an IGP type protocol, and they wrote this viewer that basically can replay these messages and to simulate or the RCS framework and the OSPF viewer. They used a dual 3.2 gigahertz Pentium 4 with 8 gigs of RAM. It had Linux kernel 2.65, and it basically they leveraged a Quagga BGP implementation for testing, and they extended this framework for the RCS. And the routing emulator was actually a 1 gigahertz Pentium 3 that had 1 gig of RAM and a Linux kernel 2.4.22. So some of the results were interestingly that this was specifically to BGP. We can see that this RCP had linear growth in the memory growth for a number of groups in prefixes, and the map or the image on the graph on the left shows group sizes going from 0 to 10, actually from 1, sorry, from 1 to 10 to 100, and how much memory it would consume. And we could see that for 200,000 203,000 of prefixes with the groups with having 100 groups, that translates into roughly 2.2 gigabytes of RAM, which is fairly reasonable. And we can see that BGP update rates were varied significantly, anywhere from 6 messages per second to well over 100 messages per second, and this was quite sporadic. And one of the other observation was that this RCP framework is able to very quickly process BGP message updates. And when there is a very quick or fast flood of these messages, then RCP or RCP framework it tends to have a queuing problem, at least with the RCS. Um, and which we're gonna see on the next slide in more detail. So a single IGP path update can have a domino effect. And remember that we're talking about the OSPF floods. Um, for example, a path gets withdrawn, and this can trigger an effect on a neighboring router, which can trigger more effects and so on. And because there is large number of routers, especially more recently with bigger networks, like bigger size networks, this can have a very bad or severe domino effect. And so testing OSPF, as reading that section, OSPF events, they have, again, high likelihood of route recalculations depending on type of event update um, that showed there is increase in processing time. So a significant portion of computational cost is attributed to this OSPF path cost changes. So IGP portion is quite the biggest, one of the biggest computational cost for this framework. And this suggests that RCS is susceptible to queuing effects. And they pointed out that this is indeed a hard problem, and vendors take various shortcuts. And for example, we can see that some vendors do not execute BGP decision process after IGP event. Instead, what they do is they resort to performing periodical scan of BGP routing tables and to revisit the routing decision for each destination prefix. Another example is that some vendors of commercial routers scan BGP routing table once every so many seconds, for example 60 seconds, and introduce the possibility of long inconsistencies across routers that cause forwarding loops and persistent for tens of seconds. And as we see, even commercial solutions have a bunch of shortcuts. One of the solution that they suggested was not to react to all path cost changes. This essentially resulted in dramatic reduction of processing time. Significant improvement, but then again you have to be able to intelligently select which paths updates to react, which are not to react. So some of the takeaways. I don't know. I was reading their consistency protocol, how to maintain consistency when there are multiple components in a network, especially their. Let's see, where was there? Okay, so if there's multiple RCSs in a network, I didn't really feel too comfortable that there was a really good solution that they presented that guaranteed consistent behavior. Having a single one would probably suffice, and I think probably the best way to guarantee consistent behavior. Another point, I was not quite sure on how to interpret selectively filtered data in their testing section. Also, it would be interesting if they did the full end-to-end comparison as opposed to just component testing. Also, it would be interesting to test this platform on today's traffic, how well it really, if this is indeed a solution, a good solution to this problem. According to their analysis, also, there is no need to run a separate consistency protocol. I don't know. I wasn't quite sure about this statement. Not sure about testing on one day on a single or using a single day tester. This platform would be sufficient. And lastly, I don't know. It's just my own observations. Again, it seems like a lot of these papers I was reading regarding the routing scalability table looks like a fairly old problem, and many good solutions were being presented. But I was just curious how much of these solutions are actually being adapted, and why many of them did not take off. And thank you for. If you have any questions, please feel free to ask. StuskEV at clarkson.edu. That's my email.